Solar irradiance is the power per unit area produced by the Sun in the form of electromagnetic radiation. Irradiance may be measured in space or at the Earth's surface after atmospheric absorption and scattering. Total solar irradiance is a measure of the solar radiative power per unit area normal to the rays incident on the Earth's upper atmosphere. The solar constant is a conventional measure of mean Tsi at a distance of 1 astronomical unit. Irradiance is a function of distance from the Sun, the solar cycle, and cross-cycle changes. Irradiance on Earth is most intense at points directly facing the Sun. Insolation. The solar irradiance integrated over time is called solar irradiation, solar exposure or insolation. However, insolation is often used interchangeably with irradiance in practice. Units. The SI unit of irradiance is watt per square meter. An alternate unit of measure is the Langley per unit time. The solar energy business uses watt-hour per square meter divided by the recording time. 1 kilowatt per square meter equals 24 kilowatt-hours. Irradiance can also be expressed in suns, where 1 sun equals 1000 W per square meter at the point of arrival. Absorption and reflection. Part of the radiation reaching an object is absorbed and the remainder reflected. Usually the absorbed radiation is converted to thermal energy, increasing the object's temperature. Man-made or natural systems, however, can convert part of the absorbed radiation into another form such as electricity or chemical bonds, as in the case of photovoltaic cells or plants. The proportion of reflected radiation is the object's reflectivity or albedo. Projection effect. Insolation onto a surface is largest when the surface directly faces the Sun. As the angle between the surface and the Sun moves from normal, the insolation is reduced in proportion to the angle's cosine. See effect of Sun angle on climate. In the figure, the angle shown is between the ground and the sunbeam rather than between the vertical direction and the sunbeam, hence the sine rather than the cosine is appropriate. A sunbeam 1 mile wide arrives from directly overhead, and another at a 30 degrees angle to the horizontal. The sine of a 30 degrees angle is 1/2, whereas the sine of a 90 degrees angle is 1. Therefore, the angled sunbeam spreads the light over twice the area. Consequently, half as much light falls on each square mile. This projection effect is the main reason why Earth's polar regions are much colder than equatorial regions. On an annual average, the poles receive less insolation than does the equator, because the poles are always angled more away from the Sun than the tropics. At a lower angle, the light must travel through more atmosphere. This attenuates it further, reducing insolation. Categories. Direct insolation is measured at a given location with a surface element perpendicular to the Sun. It excludes diffuse insolation. Direct insolation is equal to the solar constant minus the atmospheric losses due to absorption and scattering. While the solar constant varies, losses depend on time of day, cloud cover, moisture content and other contents. Insolation affects plant metabolism and animal behavior. Diffuse insolation is the contribution of light scattered by the atmosphere to total insolation. Earth. Average annual solar radiation arriving at the top of the Earth's atmosphere is roughly 1366 W per square meter. The radiation is distributed across the electromagnetic spectrum, although most is visible light. The Sun's rays are attenuated as they pass through the atmosphere, leaving maximum normal surface irradiance at approximately 1000 W per square meter at sea level on a clear day. The actual figure varies with the Sun's angle and atmospheric circumstances. Ignoring clouds, the daily average insolation for the Earth is approximately 6 kilowatt-hours per square meter equals 21.6 megajoules per square meter. The output of, for example, a photovoltaic panel, partly depends on the angle of the Sun relative to the panel. 1 sun is a unit of power flux, not a standard value for actual insolation. Sometimes this unit is referred to as a sol, not to be confused with a sol, meaning 1 solar day. Solar potential maps North America, South America, Europe, Africa and Middle East, South and Southeast Asia, Australia. Top of the atmosphere. The distribution of solar radiation at the top of the atmosphere is determined by Earth's sphericity and orbital parameters. This applies to any unidirectional beam incident to a rotating sphere. Insolation is essential for numerical weather prediction and understanding seasons and climate change. Application to ice ages is known as Milankovitch cycles. Distribution is based on a fundamental identity from spherical trigonometry, the spherical law of cosines, where A, B and C are arc lengths, in radians, of the sides of a spherical triangle. C is the angle in the vertex opposite the side which has arc length C. Applied to the calculation of solar zenith angle theta, the following applies to the spherical law of cosines. The separation of Earth from the Sun can be denoted ρ and the mean distance can be denoted r0, approximately 1 astronomical unit. The solar constant is denoted S0. The solar flux density onto a plane tangent to the sphere of the Earth but above the bulk of the atmosphere is, and the average of Q over a day is the average of Q over one rotation, or the R angle progressing from h equals pi to h equals minus pi. Let h0 be the R angle when Q becomes positive. This could occur at sunrise when, or for h0 as a solution of or if tantan greater than 1, then the sun does not set and the sun is already risen at h equals pi, so ho equals pi. If tantan less than minus 1, the sun does not rise and is nearly constant over the course of a day, and can be taken outside the integral. Let theta be the conventional polar angle describing a planetary orbit. Let theta equals 0 at the vernal equinox. The declination delta as a function of orbital position is where epsilon is the obliquity. The conventional longitude of perihelion is defined relative to the vernal equinox, so for the elliptical orbit, or with knowledge of epsilon and e from astrodynamical calculations and so from a consensus of observations or theory, can be calculated for any latitude phi and theta. Because of the elliptical orbit, and as a consequence of Kepler's second law, theta does not progress uniformly with time. Nevertheless, theta equals 0 degrees is exactly the time of the vernal equinox, theta equals 90 degrees is exactly the time of the summer solstice, theta equals 180 degrees is exactly the time of the autumnal equinox, and theta equals 270 degrees is exactly the time of the winter solstice. Variation. Total irradiance. Total solar irradiance changes slowly on decadal and longer timescales. The variation during solar cycle 21 was about 0.1%. In contrast to older reconstructions, most recent TSI reconstructions point to an increase of only about 0.05% to 0.1% between the Maunder minimum and the present. Ultraviolet irradiance. Ultraviolet irradiance varies by approximately 1.5% from solar maxima to minima, for 200 to 300 nanometers wavelengths. However, a proxy study estimated that UV has increased by 3.0% since the Maunder minimum. Milankovitch cycles. Some variations in insolation are not due to solar changes but rather due to the Earth moving between its perigee and apogee, or changes in the latitudinal distribution of radiation. These orbital changes or Milankovitch cycles have caused radiance variations of as much as 25% over long periods. The most recent significant event was an axial tilt of 24 degrees during boreal summer near the Holocene climatic optimum. Obtaining a time series for a particular time of year, and particular latitude, is a useful application in the theory of Milankovitch cycles. For example, at the summer solstice, the declination delta is equal to the obliquity epsilon. The distance from the Sun is for this summer solstice calculation. The role of the elliptical orbit is entirely contained within the important product, the precession index, whose variation dominates the variations in insolation at 65 degrees north when eccentricity is large, for the next 100,000 years, with variations in eccentricity being relatively small. Variations in obliquity dominate measurement. The space-based TSI record comprises measurements from more than 10 radiometers spanning 3 solar cycles. Technical modern TSI satellite instruments employ active cavity electrical substitution radiometry. This technique applies measured electrical heating to maintain an absorptive blackened cavity in thermal equilibrium while incident sunlight passes through a precision aperture of calibrated area. The aperture is modulated via a shutter. Accuracy uncertainties of less than 0.01% are required to detect long-term solar irradiance variations, because expected changes are in the range 0.05 to 0.15 Wm-2 per century. Intertemporal calibration in orbit. Radiometric calibrations drift for reasons including solar degradation of the cavity, electronic degradation of the heater, surface degradation of the precision aperture, and varying surface emissions and temperatures that alter thermal backgrounds. These calibrations require compensation to preserve consistent measurements. For various reasons, the sources do not always agree. The Solar Radiation and Climate Experiment Total Irradiance Measurement TSI values are lower than prior measurements by the Earth Radiometer Budget Experiment on the Earth Radiation Budget Satellite Virgo on the Solar Heliospheric Observatory and the ACRIM instruments on the Solar Maximum Mission Upper Atmosphere Research Satellite Inaccuracies. Pre-launch ground calibrations relied on component rather than system-level measurements, since irradiance standards lacked absolute accuracies. Measurement stability involves exposing different radiometer cavities to different accumulations of solar radiation to quantify exposure-dependent degradation effects. These effects are then compensated for in final data. Observation overlaps permits corrections for both absolute offsets and validation of instrumental drifts. Uncertainties of individual observations exceed irradiance variability. Thus, instrument stability and measurement continuity are relied upon to compute real variations. Long-term radiometer drifts can be mistaken for irradiance variations that can be misinterpreted as affecting climate. Examples include the issue of the irradiance increase between cycle minima in 1986 and 1996, evident only in the ACRIM composite, and the lower radiance levels in the PMOD composite during the 2008 minimum. Despite the fact that ACRIM-I, ACRIM-2, ACRIM-3, Virgo and TIM all track degradation with redundant cavities. Notable and unexplained differences remain in irradiance and the modeled influences of sunspots and factly. Persistent inconsistencies. Disagreement among overlapping observations indicates unresolved drifts that suggest the TSI record is not sufficiently stable to discern solar changes on decadal timescales. Only the ACRIM composite shows irradiance increasing by 1 Wm-2 between 1986 and 1996. This change is also absent in the model. Recommendations to resolve the instrument discrepancies include validating optical measurement accuracy by comparing ground-based instruments to laboratory references, such as those at National Institute of Science and Technology. NIST validation of aperture area calibrations uses spares from each instrument, and applying diffraction corrections from the view-limiting aperture. For ACRIM, NIST determined that diffraction from the view-limiting aperture contributes a 0.13% signal not accounted for in the 3 ACRIM instruments. This correction lowers the reported ACRIM values, bringing ACRIM closer to TIM. In ACRIM and all other instruments, the aperture is deep inside the instrument, with a larger view-limiting aperture at the front. Depending on edge imperfections, this can directly scatter light into the cavity. This design admits 2 to 3 times the amount of light intended to be measured, if not completely absorbed or scattered. This additional light produces erroneously high signals. In contrast, TIM's design places the precision aperture at the front so that only desired light enters. Variations from other sources likely include an annual cycle that is nearly in phase with the Sun-Earth distance in ACRIM3 data and 90-day spikes in the Virgo data coincident with SOHO spacecraft maneuvers that were most apparent during the 2008 solar minimum. Tsi Radiometer Facility. TIM's high absolute accuracy creates new opportunities for measuring climate variables. Tsi Radiometer Facility is a cryogenic radiometer that operates in a vacuum with controlled light sources. L1 Standards and Technology designed and built the system, completed in 2008. It was calibrated for optical power against the NIST primary optical watt radiometer, a cryogenic radiometer that maintains the NIST radiant power scale to an uncertainty of 0.02%. As of 2011, TRF was the only facility that approached the desired less than 0.01% uncertainty for pre-launch validation of solar radiometers measuring irradiance at solar power levels and under vacuum conditions. TRF encloses both the reference radiometer and the instrument under test in a common vacuum system that contains a stationary, spatially uniform illuminating beam. A precision aperture with area calibrated to 0.0031% determines the beam's measured portion. The test instrument's precision aperture is positioned in the same location, without optically altering the beam. For direct comparison to the reference, variable beam power provides linearity diagnostics, and variable beam diameter diagnoses scattering from different instrument components. The Glory, Tim and Picard (PREMOS) flight instrument absolute scales are now traceable to the TRF in both optical power and irradiance. The resulting high accuracy reduces the consequences of any future gap in the solar irradiance record. 2011 reassessment. The most probable value of TSI representative of solar minimum is 1360.8 plus or minus 0.5 Wm-2, lower than the earlier accepted value of 1365.4 plus or minus 1.3 Wm-2, established in the 1990s. The new value came from SORCE, TIM and radiometric laboratory tests. Scattered light is a primary cause of the higher irradiance values measured by earlier satellites in which the precision aperture is located behind a larger view-limiting aperture. The TIM uses a view-limiting aperture that is smaller than precision aperture that precludes this spurious signal. The new estimate is from better measurement rather than a change in solar output. A regression model-based split of the relative proportion of sunspot and facular influences from SORCE, TIM data accounts for 92% of observed variance, and tracks the observed trends to within TIM's stability band. This agreement provides further evidence that TSI variations are primarily due to solar surface magnetic activity. Instrument inaccuracies add a significant uncertainty in determining Earth's energy balance. The energy imbalance has been variously measured to be plus 0.58 plus or minus 0.15 W per square meter, plus 0.60 plus or minus 0.17 W per square meter and plus 0.85 Wm-2. Estimates from space-based measurements range from plus 3 to 7 Wm-2. SORCE, TIM's lower TSI value reduces this discrepancy by 1 Wm-2. This difference between the new lower TIM value and earlier TSI measurements corresponds to a climate forcing of minus 0.8 Wm-2, which is comparable to the energy imbalance. 2014 reassessment. In 2014, a new ACRIM composite was developed using the updated ACRIM3 record. It added corrections for scattering and diffraction revealed during recent testing at TRF and 2 algorithm updates. The algorithm updates more accurately account for instrument thermal behavior and parsing of shutter cycle data. These corrected a component of the quasi-annual signal and increased the signal-to-noise ratio, respectively. The net effect of these corrections decreased the average ACRIM3 TSI value without affecting the trending in the ACRIM composite TSI. Differences between ACRIM and PMOD TSI composites are evident, but the most significant is the solar minimum to minimum trend during solar cycles 21 to 23. ACRIM established an increase of plus 0.037% decade from 1980 to 2000 and a decrease thereafter. PMOD instead presents a steady decrease since 1978. Significant differences can also be seen during the peak of solar cycles 21 and 22. These arise from the fact that ACRIM uses the original TSI results published by the satellite experiment teams, while PMOD significantly modifies some results to conform them to specific TSI proxy models. The implications of increasing TSI during the global warming of the last 2 decades of the 20th century are that solar forcing may be a significantly larger factor in climate change than represented in the CMIP5 general circulation climate models.